All right. Welcome to the first lecture of CS250B, Modern Computer Systems. In the first lecture today, we're not going to cover too much information about the systems themselves. We're going to spend a little bit of time kind of setting the stage for why we need to talk about this at this day and age. And most of the slides here, some of you may have seen a little bit. I really like talking about this particular deck of slides, be it my ad hoc talks or undergrad or graduate level slides. But hopefully this will be a little bit interesting. All right. In the olden days, with conventional performance scaling of computers, the traditional model of a computer used to be very simple. We have a CPU, we have a memory connected to it. Program and data are both sitting on the memory, and the CPU just talks to the memory doing computation. Reads program from the memory, reads data from the memory, does some computations, writes back some data to the memory. From the CPU point of view, a program is a single in-order flow of instructions on a processor. Nothing special, just one program counter moving forward. And also from the CPU point of view, the memory used to be a simple in-order memory model, a single unified address space, et cetera, et cetera. So basically a simple model where a single thread in a CPU talking to a monolithic memory. And that worked for a long time. I mean, it worked very well for a very long time. And because this model is very simple to work with, and all the programmers would rather work with this abstraction than anything else, a large part of computer architecture research have involved maintaining this abstraction while improving performance. Maintaining this abstraction of a single CPU thread, or at least a handful of CPU threads, talking to a simple uniform address space, but making the performance improve under the hood. So things like transparent caches, transparent superscalar scheduling, out-of-order processors, all that stuff, which were very important and big hits in the computer architecture area, were attempts to improve the performance of the computer without making the programmer be aware or need to care about the underlying improvements that are going on. And the benefits to this was that the same software that someone wrote today was going to run faster tomorrow, because we're going to have faster computers, better machines tomorrow. And of course, if we had written very slow software today, it may become kind of acceptable tomorrow, because again, the CPU and the memory and everything is going to become faster. That was good for a while. And admittedly, it wasn't a very important time to be doing computer architecture research, because the big world-shaking things that I was working on, unless it was just completely free to use and brought something like 10 times performance improvements, people are going to say, why should I put in the effort migrating to your architecture when the same Intel x86 is going to become just as fast in 2 years? Without us having to edit the software or anything. And we're going to get to that in a little bit. But the reason that all of this, one of the big reasons that all of this was possible for a very long time, was driven largely by the continuing march of Moore's law. And I guess we would like to spend just a little bit of time going over what exactly Moore's law is before we go on to other topics. Because what exactly does Moore's law mean? And what is it that is scaling inside Moore's law? And a lot of people seem to give slightly misguided answers when we talk about this. So I'd like to spend just a little bit of time talking about it. So Moore's law is typically cast, when you ask people about what is Moore's law, it is typically cast as performance doubles every X months. And that's not far from the truth. But the closer meaning to what exactly Moore's law means, and this is going to become important in a bit, is that the number of transistors per unit cost doubles every X months. So there's a subtle difference between the performance doubling every X months and the number of transistors per unit cost per unit area doubling every X months. And this is actually pretty clear from the original interview with Gordon Moore back in 1965, when he actually put forth this thing for the first time. The complexity of a minimum component cost has increased at a rate of roughly a factor of 2 per year, which has continued for a few decades at least. And he also goes on to say over the longer term, the rate of increase is, of course, it's a bit more uncertain, but there's no reason to believe it will not remain nearly constant for at least 10 years. And seeing that this prediction was made in 1965, this was a pretty accurate assessment of what was going to come. So the small question here is, why is Moore's law conflated so much with processor performance when it at least initially meant scaling of transistor count per cost? So there's a second factor to this called Dennard scaling, which is the thing that at least used to translate Moore's law to performance. And the gist of Dennard scaling put forth by Robert Dennard is that power density of an integrated circuit stays constant as transistors get smaller. Moore's law is what makes transistors get smaller. Dennard scaling is the thing that lets the power density of the chip stay the same, even as transistors get smaller. And as long as these two things hold, intuitively, and there's a lot more complexity to this, but I guess we don't want to go too deep into the EE weeds, is that once you have smaller transistors, distance between transistors are going to become shorter on average, which leads to shorter propagation delay. And shorter propagation delay between transistors means we can hit faster maximum frequency of the clock. So faster clock with smaller transistors, which leads to faster performance. On the other hand, we can also have, if we have smaller transistors, at least for a while, smaller transistors also meant smaller capacitance per transistors. So smaller capacitors means that we can afford to have a smaller voltage, smaller supply voltage, while maintaining the same clock frequency. We require a lower amount of voltage to switch a single transistor back and forth. So given these two things, and the fact if we look at a very simplified model of power consumption inside a circuit, the power consumption of a circuit has to do with the capacitance of the circuit multiplied by the square of the voltage of the circuit multiplied by the frequency of the circuit. So let's see. Because as Moore's law makes transistors smaller, capacitance goes down. Let me move this character. Capacitance goes down with smaller transistors. Voltage goes down with smaller transistors. So that means as we get smaller transistors, we could afford to increase the frequency of the clock frequency of the chip without increasing the power consumption. So this is what led Moore's law to achieve faster performance at constant power. And this worked for a very, very long time. It worked from back in the 60s all the way up to very recent history. And to the point that some people, and this is a chart from back into the early 2000s, to make predictions like this. And this chart, this was from IBM and Intel. X-axis is the time, scaling from the 70s all the way up to 2020s. Y-axis is the clock frequency, or at least projected clock frequency of processors, desktop server grade processors. And the clock frequency of processors scaled well enough in a manner predictive enough that people made projections back in the early 2000s that around the time we got to the year 2020, we should have had something like 100 gigahertz processor on our desktops. Unfortunately, we don't, or fortunately, or rather, unfortunately or fortunately, depending on how you look at it, we don't have 100 gigahertz processors on our desktop as of 2021. So the question here is what happened? So here we'll go just a little bit into the weeds of these power consumption numbers. So the power consumption equation that I showed a couple of slides ago is a vastly simplified version. So let's go just a little bit more into the details. So the power consumption of a circuit has to do with the number of transistors that are firing, that are working, switching back and forth, multiplied by the capacitance, multiplied by the square of the voltage, multiplied by the frequency, clock frequency. And this is only half of the equation. This part is called the dynamic power consumption. And this has to do with the power consumption involved in switching transistors back and forth. That's why it has a factor called active transistors. If a transistor is just sitting there holding the value of the same value across every clock cycle, it will not have much dynamic power. The other part of the equation is static power. And static power is sometimes also called leakage power, is energy that is consumed even when the circuit is not doing anything. As long as the transistors are connected to a voltage input, it is leaking this much power. And the static power is calculated as a multiplication between the supply voltage and what is called a leakage. And if we look at a super simplified version of how to calculate leakage current, leakage is calculated by the inverse exponent of the voltage. So static power is calculated by proportional to voltage, also inverse exponent proportional to the voltage. So this might not make too much sense right now, but if we push forward just a little bit more, we're going to show how because the leakage power is proportional to the inverse exponent, meaning as voltage becomes smaller and smaller, leakage current can increase exponentially fast. So because of this, we cannot continue to scale voltage down indefinitely, because at some point, the static power consumption is going to overtake dynamic power consumption in its amount. And because there's an exponent here, once static power consumption does overtake dynamic power consumption, it's going to completely dominate very quickly. So there's only a certain amount of, we can only go down to a certain point when we scale down voltage. On top of that, the capacitance of a circuit kind of stopped scaling as well as the size of transistor components became smaller and smaller. Which is this a good time to say this? Yeah, which means regardless of the size of the transistors becoming smaller and smaller, the capacitance is no longer becoming smaller. The voltage part is also no longer becoming smaller, which means we cannot continue scaling frequency at a constant power budget anymore. We're going as we continue scaling frequency in the modern world, the power consumption is going to increase along with it, unlike how it was at least until the early 2000s. And to kind of illustrate that point a little bit, here's a chart with that overlays the green line. The green line is the dynamic power consumption. As the x-axis, the voltage increases. The red line is the static power consumption, as also voltage increases. So if we can continue scaling voltage down for whatever reason, dynamic power consumption, which is the green line, is going to continue scaling down. But at some point, because of the inverse exponent in the leakage current, if we bring down voltage a little bit too much, static power consumption is going to exponentially increase. So there's a point in which we can achieve minimum power consumption by balancing the dynamic and static power consumptions. But if we go down further, even if we could reduce the power voltage level of the transistors as transistors become smaller, there's a point that it's not going to bring us any more power saving benefits. So that is what's typically denoted as the end of Dennard scaling. And as we saw before, Dennard scaling was a key factor in translating Moore's law, the transistor density brought about by Moore's law, translating that into performance. So Dennard scaling stopped around 2006, and we're going to show that chart in a little bit as well. But the bottom line was that even with smaller transistors, we cannot continue reducing the power consumption of the circuits. And what could we have done at this point? One option to continue scaling performance, because we always want more performance, one option to continue scaling performance in light of Dennard scaling ending would be to continue scaling frequency at an increased power budget. Yeah, we can continue scaling frequency. Yes, it's going to require more power, but we'll just plug in a better power source, bigger power source, bigger heat sinks. The problem here was that the chip quickly becomes way too hot to cool, compounded by a thing called the thermal runaway. The resistance of silicon increases with temperature. So if we can't keep the temperature of the chip down to a certain level, once we have a hotter chip, the capacitance of the chip will also increase, which leads to a hotter chip, which leads to the increased capacitance, resistance of the chip, so on and so on, until it becomes way too hot for conventional or even reasonable cooling systems to be able to handle. And here's a very famous chart, which was put out by Intel back in 1999. If we had continued scaling the frequency of the processor while just eating the increased power budget, by the time, the projection was that by the time the processor manufacturing technology reached, let's see, 100 nanometers, the power density of the chip would have reached the levels of a nuclear reactor. And this is, I guess, we don't want this kind of a thing on our desktops. And if we had continued this ad infinitum, right now we're somewhere around the technologies of 7 nanometers production. And if we had reached 7 nanometers while just continuing to scale frequency, the power density of our desktop would be somewhere around the levels of a rocket nozzle. Considering how let's say, when the Saturn V rocket blasted off trying to reach the moon, the engine kind of vaporized a couple of feet, at least a couple of inches of raw concrete under it on the launch pad. I would say this is not something we wanted on our desktop. So this was an infeasible thing to do because we're not going to be cooling rocket nozzle levels of heat density with a fan or a heat sink or anything, even liquid cooling, whatever. So what's the second option? The second option is to stop frequency scaling because there's really no other choice. And if you look at the clock frequencies of desktop and server grades processors that were released and sold over time, x-axis is time, scaling from 1985 to 2010s, you can pretty much see when exactly Dennard scaling stopped and processor frequency scaling became not feasible. And it was almost pinpointed around the year 2006. So you can see that the clock frequency of the CPUs that are sold on the market have kind of plateaued since then. And this is just the reality that we're living in. And the question here becomes, how do we deal with it? And if you look back on the predictions that people have made and how that's changed over time, let's see, the sharp blue line here is the prediction. So x-axis is time, y-axis is the clock frequency of the chip. The sharp blue line here was the projection made in 1999. The projection was that the clock frequency is going to increase exponentially as time went on, because y-axis is exponential scale, at least until year 2010s or so. And as time went on, So the green line here was projection made in 2001. The orange line here was projection made in 2004. The peach line here is projection made in 2012. And you can see that the projection for the speed of clock frequency scaling has adjusted a little bit more realistically as time went on. And yeah, it's safe to say that we didn't hit the happy ideal futures where we were having 100 gigahertz CPUs on our desktops, at least with reasonable cooling technologies. So yes, the state of the world here is that we are not getting faster processors, at least in terms of clock frequencies. But the thing is, Moore's law, Dennard scaling stopped around 2006, but Moore's law does continue beyond 2006. X-axis is time here again. And if you look at the number of transistors that are on chips that are sold, the transistor count is still kind of scaling. Even this is slowing down now, but it has scaled for a much longer time after Dennard scaling kind of broke down. So what's the best way to move forward from here? So if you look back at the state of things at this point, back in 2006, single thread performance scaling is effectively ended. First, because the frequency scaling ended, because Dennard scaling has ended. And incidentally, also around 2005, 2006, instruction level parallelism scaling also stalled. And you can see the chart here. The purple line here is the instruction level parallelism. Instruction level parallelism, to give a little bit of a jog on your memory about what it is from the computer architecture lectures, is the number of instructions, parallelism that can be extracted from a single stream of instructions automatically by the processor. So even if the programmer writes a single thread program, it is possible for the processor to use technologies like pipelining, superscalar, out of order, et cetera, to extract a little bit of fine-grained parallelism from it. But unfortunately, and that worked for a while with technologies like pipelining and out of order processing being introduced into modern processors. But the parallelism that can be extracted from that kind of an approach, taking a single thread program software and extracting parallelism from it, has also kind of stalled around 2005-ish. And of course, if some genius comes along next year and discovers the next out of order processing paradigm, then this could change, but so far it seems that it hasn't. Despite the fact that single thread process performance scaling has ended around 2006 due to the end of frequency scaling, due to the end of ILP scaling, Moore's law still does continue. Transistor count per unit cost is doubling every 2 years. And the question becomes, what do we do with them to try to get better performance and end-to-end better performance? So one popular solution to this, a solution which we are kind of accepting as our world now, is many cores. Instead of creating single powerful cores that continues performance scaling on its own, people started building smaller, weaker processors, but more of them that could fit on the processor. So after we had the Pentium, at least if we look at the Intel timeline, after we had the Pentium 4 processor, instead of continuing the single core performance scaling, Intel came out with the Core 2 Duo processor, which was a dual core processor without increasing the single thread performance. And by doing this, because we stopped scaling clock frequencies, we managed to turn around in terms of the heat density of the processor before we hit nuclear reactor levels of power density. So that was good. And this approach worked for a while. And I would say it is still kind of working. The approach of using the exponentially increasing number of transistors to build multi-cores. And there was a lot of research and a lot of industry and academic research involving how to better manage these many cores, how to program these many cores, et cetera, architectural solutions to making them work more efficiently. It was a fun time. And I guess as these things do, because people predicted that this approach of having many cores is going to work indefinitely into the future, it prompted people to create charts like this. This is a chart from ITRS back in 2007, projecting the scale of the number of cores we're going to have on consumer desktop server class machines as time went on. X-axis is time as usual. Y-axis is the number of cores on the chip. And if this scaling had continued as projected, at around 2018, we should have had desktop class machines with more than 100 cores on our CPUs. Unfortunately, that's has not happened. Even our pretty good desktop machines that we can buy right now typically have something along the lines of 6 to 8 cores. I guess you could say that this projection has kind of been met by the advent of GPU-based computing technologies, but I have a feeling that that wasn't what the ITRS folks were talking about when they created this chart. So this hasn't happened as well. This number of core scaling hasn't happened as well. And what happened? Why didn't we hit that goal? For this, there's multiple reasons, multiple very prominent reasons, but since we were looking at power consumption numbers before, we can spend a little bit more time looking at power consumption numbers. So in the total power consumption equation, all these colored blocks are the things that have stopped scaling. Capacitance stop scaling, voltage stop scaling, frequency stop scaling. So the only thing that's left used to be the number of active transistors, meaning the number of transistors that are doing actual work. The problem is, even this can't keep going up, because as active transistors kept going up, that has a direct proportional impact on the amount of power consumption. And of course, if we have a hard power budget envelope that we need to fit inside, then regardless of Moore's law, only a limited amount of transistors can be active at a given time, regardless of whether Moore's law brings us an exponential scaling in the number of transistors. Even if we had something like 5 bajillion transistors on our chip, only a certain limited number of those transistors can be active at a given time within the power budget. And this is what's called the utilization wall. And there are multiple reasons beyond the utilization wall why the many-core approach hasn't scaled as fast as ITRS had predicted. Not the least of them being ITRS was just not good at predicting that to that precise extent. But anyways, so this is the state of the world that we are in right now. The number of active transistors given at a time is limited. And if we just keep living in this world without doing anything special, we won't get much performance improvements from Moore's law, even if Moore's law was able to indefinitely give us scaling in terms of the number of transistors. So at least the short-term solution seems to be, unless we get something drastically different like quantum computers or graphene or whatever next year, the short-term solution seems to be that we need to make the absolute best use of these active transistors, because the number of transistors that we're going to get working at any given point in time is pretty much fixed. So you have to figure out a way to make use of those things more efficiently. And to pile on to this problem further, even scaling in terms of Moore's law is becoming more difficult. And this is basically what Moore's law is. Processor fabrication technology has always reduced in size over time. As of the end of 2020, 7 nanometers seems to be kind of cutting edge across all these companies. And they're collectively working towards 5 nanometers and 3 nanometers and onwards. So things have become smaller and smaller. But even that seems to be becoming quite hard. There are multiple indicators that can show this. But one thing that could jump out is if you look at the number of companies, a number of fabrication plants that have had production capabilities in these. So the x-axis here is the manufacturing technology, scaling from something like 65 nanometers all the way to 7 and 5 nanometers. Y-axis is the list. Sorry. Y-axis is the list of companies and fabrication plants that have had this technology. So back in when the process size was very large, there was a lot of companies that could pull off doing processor fabrication. But as technology became harder and harder, it seems that there's at best only 3 players left. Maybe GlobalFoundries will come back with 5 nanometers, but at least right now, Samsung, TSMC, and Intel seem to be the only players left in the market for at least attempting to do 5 nanometer process and onwards. So it is becoming harder to do this. So given that this is the world that we are living in right now, what can we do as engineers, researchers, programmers, and architects? And this is where this course comes in as a kind of a high-level introduction. Number one potential solution, the first potential solution, is the software solution, at least from the context of this course. The software solution is to write efficient software to make the make the most efficient use of available hardware resources. So from the software programmer point of view, for the longest time, we were able to just write, we were able to focus on programmability, we were able to focus on productivity, etc., and leave the performance scaling to the hardware. And it seems that the world has changed a little bit so that it might become necessary to no longer depend entirely on hardware performance scaling. And software developers need to actually spend time and effort learning about the underlying architectural caveats and optimizing towards them. This is what is called performance engineering software using hardware knowledge. And that's potential solution number one that we're going to deal with quite heavily in this course. And here's an example that I really like to give. And I give this example to everyone in every talk, every course, and every person I meet at conferences, to the point that a lot of people who know me are tired of this example. But if you look at the impact of software performance engineering in the context of, let's say, matrix-matrix multiplication, because it's one of the most important applications that are used everywhere from scientific computing to neural networks. So in your mind, try to have a guesstimate to this question. So we're going to try to multiply 2 matrices, 2048 by 2048 cells, single floating point number on each. 248 by 248 matrix is approximately 16 megabytes. It's not going to fit in smaller caches like L1, L2 caches in desktop grade machines. And I measured the performance of this matrix-matrix multiplication on my desktop where I make slides, which has an Intel i5 processor running at 3 gigahertz. So it's not the fastest Threadripper, but it is reasonable. So I tried writing the simplest matrix-matrix multiplication algorithm, the normal triple for loop, where we traverse matrix A in row measure, and traverse matrix B in column measure. Triple for loop for I, for J, for K, and does the calculation and stores it in C. So in your mind, try to have a guesstimate of how fast this will finish. Do you think it'll be less than 10 seconds? Do you think it'll be more than 10 minutes? Less than 1 second? Because 16 megabytes isn't that large. I mean, it could fit in a bunch of floppy disks. So the answer to this question, at least on my desktop, is that it takes a minute-ish to run this calculation, in which, depending on on your guesstimate, this could be a little bit surprising because modern computers are super fast, running at 3 gigahertz, and this tiny 16 megabyte problem is going to take a minute to process. Of course, it has a lot to do with things like, it has a time complexity of n cubed, et cetera, et cetera. And the question here is this good? Is this a numbers that we should be happy with? If we were writing a piece of software that involves matrix-matrix multiplication, and this is the performance that we get on our desktop, is this good? Can we move on to other features, or do we need to start doing performance engineering? So in comparison, here's another matrix-matrix multiplication implementation that employs a very, very simple, just one very, very simple optimization. Instead of, we're going to use the same triple for loop, but instead of traversing A row measure and B column measure, we're going to transpose B first, just one sweep over B, transposing it, so that matrix-matrix multiplication can be done by row measure traversal of both A and B transpose matrices. And just by doing this, the performance of the matrix-matrix multiplication increases sixfold almost. It only takes about 10 seconds now. And this is the kind of things that, this is the kind of performance engineering that people project is going to become necessary very soon in the future, because if our hardware isn't going to give us, this approach basically gave us 6x performance at exactly the same hardware cost. And if hardware performance per cost isn't going to continue scaling, and this is the kind of things that we need to extract performance from our problems. And at our last year's lecture, actually last time I gave this lab, we measured 42x performance improvement on a single thread implementation of matrix-matrix multiply just by writing better software. By writing single thread software without throwing any more hardware at it, we were getting 42x performance improvements in this exact same problem. And this is the kind of course, this is 42x. 42x is really, really good, but it's not, this isn't going to scale indefinitely, of course. But given the world we live in, where the cost of performance is not going to be just hardware anymore, these are things that we need to care about. So this is going to be about 1/2 of what this course is going to talk about. The second solution, not the software solution, is the specialized hardware solution, at least from my point of view. The hardware solution comes from the observation that the chip space in terms of transistors is now very cheap because of Moore's law, et cetera, et cetera. But power consumption is expensive, not because electricity is expensive, because heat density. So the solution to this could be to stop depending so much on more complex general purpose cores. So instead of building 1, 2, 4, or 8 very, very powerful, at least attempting to be very, very powerful general purpose cores, we can use that space to build heterogeneous systems in which we have multiple compute engines, small compute engines, well suited and optimized for each application. And here's an example of what that might look like. We could potentially build special purpose circuits that exploit fine-grained parallelism much better than what a single core CPU with its single or handful of ALUs can do. So here's a application example. Let's say we're calculating a gravitational force if we have two particles on a 2D plane, denoted by their x locations, y locations, and mass. And calculating gravitational force between these two particles is going to be quite simple. We calculate the distance squared between these two particles by x1 minus x2, y1 minus x2, y2 squared and then summed. And we're going to use that to divide the gravitational constant multiplied by the mass of two particles. Simple stuff, high school physics. So if we do this try to calculate this equation on a, let's say a CPU, even a pipeline CPU, things become complicated with superscalar and whatnot. So if we don't consider superscalar right now, because there are 8 math operations to do to calculate this, the answer to this one equation, it's going to take at least 8 instructions on a CPU, meaning 8 cycles on a CPU. And if we do 2 calculations, 16 cycles, 16 instructions, at least 16 cycles on a general purpose CPU. We could build a specialized data path, a specialized circuit that can calculate this single application very, very efficiently, very, very quickly. We could build a tree of ALUs, let's say, organized into pipeline stages, like this, you see on the right here. And we will have a tree of ALUs, ALU1, ALU2, ALU3, ALU4, et cetera, et cetera, et cetera, which can emit one result of this equation per cycle. Because all of this is pipelines, we can just have the values of x1, x2, y1, y2, et cetera, being fed into this pipeline at one end, and the answers coming out this end every cycle. So compared to the CPU, general purpose CPU implementation, instead of each answer coming out every 8 cycles, we can have one answer coming out each 1 cycle. So that's one way we can build very efficient special purpose computation engines which exploit fine-grained parallelism. Because from the point of view of the hardware designers, we know that calculations branches like this one, calculation branches like this one, do not depend on each other and parallelism can be extracted from it. And not only this, the computation performance improvements of special purpose circuits comes from 2 dimensions, at least. One is this. One is that each core can be more efficient compared to general purpose processors. The other is that specialized circuits, because they're not bogged down by, what happened? Right. They're not bogged down by the need for general purpose overhead, such as instruction decoding or caches, or, well, they might need caches, but at least not transparently managed caches like the ones in the CPUs. So all of these things can go away, which means transistor usage per core is also much, much lower, meaning much more cores can fit on a chip and much lower power consumption per unit, per core. And this is the approach taken by a wide range, and we're going to get into that in a little bit, a wide range of specialized accelerators spanning from things like regular old GPU-based accelerators to the Google TensorFlow processing engines. We're actually going to spend a little bit of time on that in a couple of lectures. So if you look at the bottom line power consumption numbers of building comparison against a general purpose processor against a optimized compute engine, at least in this one instance, and my experience is that typically the reality is even better in favor of optimized compute cores. But because of things like the power consumption of doing the actual computation, the data path, increases significantly. Power efficiency becomes exponentially better with optimized cores. We may need the data cache because data caches are useful, but things like the instruction cache, the fetch and decode units, and the register file, etc., we don't need any of that when we are building a bespoke optimized core for a particular application, which resulting in an order of magnitude, it says 11x here, order of magnitude performance, power efficiency improvements over general purpose cores. So that's good. That's at least a second prominent answer to what we can do in light of the current problems. And there's quite a wide spectrum of specialized hardware that are available, spanning from more general and I guess less efficient processors, all the way to more specialized and more efficient most of the times hardware, spanning from multi-core CPUs, which are the most general. It can do anything, including booting operating systems, etc., all the way to building bespoke chips that we actually fabricate from places like TSMC and plug onto a specialized circuit board. There are multiple other offerings in the middle, things like the general purpose GPUs, using things like CUDA on NVIDIA GPUs to do things, or what is called field programmable gate arrays, FPGAs, which also sit in the middle of general purpose and application specific circuits. And typically, as we go to more specialized circuits, specialized implementations, we typically get better power efficiency. And of course, as we go to more specialized implementations, the effort we as programmers need to put in to actually get something working also increases accordingly as well. And this is the second part we're going to focus on in this course. The bottom line is the architecture from the point of view, if we had to just pick one bottom line, the architecture of our machine from the point of view of software programmers is no longer transparent. First of all, writing optimized software requires architectural knowledge. Why did the matrix multiplication example before manage to get 6x performance just by transposing? Requires architectural knowledge to evaluate and plan. How did we get 40x performance on top of that? And all of that required architectural knowledge. Of course, on top of that, special purpose quote unquote accelerators like GPUs and FPGAs are programmed explicitly. These things are not going to transparently take a single threaded implementation and make it faster magically. You have to write special software and special languages in special on special hardware abstractions to get these things working. And to try to overcome these performance problems, even general purpose processors are implementing specialized instructions that you need to use explicitly to extract more performance out of these processors. Things like single instruction multi-data, SIMD instructions such as AVX. And also special purpose instructions like AES-NI, which are used to do accelerate operations on cryptography applications. And even general purpose processors, just because things like neural networks are so important right now, even general purpose processors like Intel processors and ARM processors, etc., are also adding specialized instructions to do neural network processing better. So the difference of writing even, let's say, the same neural network software with the knowledge of these kind of special instructions against without the knowledge of these kind of instructions is going to be night and day. It's going to be orders of magnitude difference. So this is the two big tent poles that we're going to look at. The ways of writing optimized software on modern CPUs and modern memory and modern storage systems. That's part one. Part two is going to be introductions into special purpose accelerators, including GPUs, FPGAs, and even dedicated ASIC-based accelerators. And I guess I should probably come clean here and say that just from this one quarter of us talking about splitting time between CPUs, GPUs, FPGAs, and storage and accelerators, you probably won't be able to tomorrow go out and write a highly optimized FPGA accelerator. But hopefully this can, if you weren't familiar with some of these topics before, hopefully when the time comes when you have to do something like this, you will know where to start and you will have high level knowledge about the things you have to do and things you have to avoid. All right, so that's the introduction to what we're going to talk about. Coming up is, before we go into newer technologies like FPGAs and whatnot, I guess we need to make sure that we make good use of the technology that we have on our desktop class CPUs that we probably have in front of us right now. And the topics we're going to talk about include things like SIMD instructions on our CPUs and writing cache optimized code for single and multi-threaded software, et cetera, et cetera. And this is what constitutes what is called performance engineering. And to kind of motivate the importance of performance engineering software much further, and there's multiple examples, the matrix-matrix multiplication example being one of the prominent ones. Here's an interesting personal experience. Here's a quote from a paper back in 2015 from Intel called Architecting to Achieve a Billion Requests Per Second Throughput on a Single Key Value Store Server Platform from ISCA 2015. It dealt with Intel software implementation of Memcached. If you're not familiar with Memcached, it is an in-memory software. It is a software for performing in-memory caching of things like web requests, things like database requests. The request queries and their answers are cached in memory on a machine somewhere so that every single web request that comes in from a client doesn't have to go to a database, slow database. And before this paper, and even after this paper, there has been a lot of research into writing bespoke accelerators in FPGAs and ASICs and whatnot to make Memcached go fast, because it was deemed that Memcached as an application was so simple, because it's basically just a dictionary. It's basically a hash table. It was so simple that a general purpose processor was overkill. The performance, while we are reaching maximum performance for Memcached on a general purpose processor, most of the hardware was just kind of sitting idle, not being useful. And there could be better ways to spend that silicon. So there was a lot of research building optimized hardware accelerators for Memcached prior to this paper. And these Intel engineers came out, and because being Intel engineers, they know very well about the capabilities and how to make their chips go fast. The bottom line was that their software implementation running on Intel CPUs were delivering 9x, so almost an order of magnitude performance improvement, and almost 3x system energy efficiency of the best published FPGA-based implementation. So that's quite impressive, I would say. Compared to application-optimized hardware accelerators, just by writing better software, these guys were able to achieve order of magnitude performance improvements just on existing hardware, some asterisks. Yeah, and there are multiple examples like this. There are examples of SIMD-based neural network, optimized neural network implementations that at least at some point was competing on par with GPU-based implementations, et cetera, et cetera. So it would be worthwhile to spend a little bit of time on this topic.